I did the calculations while you were serving, and this is the force diagram. You have the tennis ball going at velocity v0 at angle theta from you, and I'm estimating that from your feet to the head of your tennis racket, that's about 2.75 meters. Your initial velocity is about 40 meters a second, and we want to calculate an optimal theta, an optimal angle, because you seem to be serving at an angle that's too small. So the two forces acting on the ball would be air resistance and gravity. You have a kind of flat serve, so there's no topspin, and there doesn't seem to be any wind here. Calculate gravity, well, the force of gravity is just mass times the gravity constant, and the force of air resistance is 1/2 rho v squared CD times area. And we know CD of spheres is 4.47. It's a unitless constant, and the radius of the tennis ball is about 0.67 meters. So as an area of pi r squared, which is about 0.0141 meters. The rho of the density of the air is about 1.225 kilograms per meter squared. So that gives a force of air resistance of 0.004 velocity squared. And to find the acceleration caused from the air resistance, we divide that by the mass, which is the mass of the tennis ball is about 0.058 kilograms. So the acceleration would be about 0.07 velocity squared, and it's against the ball's motion. So now we can model the height and the distance of the ball in terms of time. The h of t, which is the height, is from physics class a simple equation from the acceleration and initial velocity. The acceleration would be the gravity constant, initial velocity would be 40 cosine theta, and your initial height would be 2.75. Now to calculate the function of distance, we need to use calculus. The acceleration, which is dv over dt, would be negative 0.07 velocity squared, as we calculated earlier. We can easily use separation of variables to make the differential equation dv over v squared equals negative dt times 0.07, and integrating that, we will get that negative 1 over v equals negative 0.07 t plus constant c. We know that your initial velocity is 40 sine theta, and we can easily calculate c as 1 over 40 sine theta. That will give you the velocity equation of 1 over 0.07 t plus 1 over 40 sine theta. Integrating that again, you get the equation for distance, which will be 1 over 0.07 times ln absolute value of 0.07 t plus 1 over 40 sine theta plus another constant c1. But since t is always positive, the ln, the value in the natural log will always be positive, and we don't need absolute values. You can easily calculate c1 to be ln of 1 over 40 sine theta over 0.07. Now, the ball hits the ground when the time equals 0, and we can easily calculate that from our height equation. Substituting, using the quadratic formula, we can find that time equals t equals 40 cosine theta minus square root of 1,600 cosine squared theta plus 53.9, the whole thing divided by negative 9.8. And this we will substitute back into the distance equation to get and then solve this for an optimal distance to find what the optimal theta is. Now, if we draw the tennis court, you want to, this dimension, the wide dimension of your tennis ball will be 18.2 meters, and the x dimension will be about 2 meters. So the total length the tennis ball will travel is about 18.3 meters. So if you set x equals 18.3 and you solve for theta, you will get your optimal theta. Now we will plug this to the calculator and see what we get. And here's the graph, and we can find its zeros using a built-in calculator function. And this gives 92 degrees. So you should be hitting the ball at a 92 degree angle. Chris, this makes so much sense.